All right, so today's topic is on big data and PySpark. And I will also talk about this during the presentation. This is very like high level on big data. Reason being, most students out of this program actually don't go straight into a big data position, but it is still important to be aware of, some of the lingo and some of the technologies that are used in this space. And as we talk about the different technologies, I'll talk about like certain caveats, things to be aware of, things to maybe you want to know, and things that are not as important. So just for some context, that's the kind of material that we're going to talk about today. In terms of the labs for this topic, you'll see that they have you download Docker and install PySpark within that. Feel free to do that if you want to. I will say most students choose to skip this section just because Docker and PySpark are not, as I mentioned, not things that you tend to use at a first job. Also, on that note, a lot of people run into errors while downloading this stuff. I will admit now that I am a Apple user, so if you're on a Windows computer, harder for me to debug. But a really good place to look for solutions to debugging your problems is actually on Slack. So if you go onto Slack, there's like a search bar on the top. You can just search PySpark and you'll see a bunch of student errors that have come up over the past, I don't know, couple of years. And below a lot of them, you have instructors answering how to fix whatever's going on. So definitely consult that. But if you do have an error and you can't figure it out, send it to me anyways, and I'll see what I can do. So on that note, one more thing about PySpark before I move on, sorry. One of the next sections, so the next section is recommendation system. One lab has you implement it in PySpark. You can do that if you like, but that data set will work on your local Jupyter notebook as well. And what that means by like it'll work on your local, we'll talk about that when we talk about PySpark. So yeah, you don't necessarily have to do PySpark right now. And yeah, it's up to you if you ever do, honestly. Any questions or thoughts about that?
So just one quick question. PySpark, if we are going to use it, it's going to be completely cloud-based?
Yeah, you can think of it as like cloud-based. You're basically running your code on a different server. And very likely this server can handle like big data better than your computer can. On that note, I know because as we're going to get to like neural networks towards the end of the mod, a lot of your computers, my computer actually has issues running neural networks too, a lot of the time. I'll be introducing, Google actually has a product that is free, and it's just Jupyter notebooks ran on their servers. And I'll actually walk you all through how to set that up when we get to that part. So no worries about that.
With C, right? What is that?
It's called Google Colab. It's basically a Jupyter notebook online. It's pretty easy to implement. The hard part is like getting your data to interact with the notebook, but I will talk about that. Any other thoughts before we get into it? All right, let's get started then. Just as an agenda, what we're gonna do, a big data overview. We're gonna talk about Mapreduce. I will say if there's any one word that you take away from this, the word would be Mapreduce. We're gonna talk about the Hadoop ecosystem and Spark or PySpark. And all of this stuff we'll cover in a little bit. So things that you won't be able to do after today, or after like going through all the material and learn even, you won't be able to write and produce Mapreduce jobs because they are written in Java. Probably you will not be proficient in end-to-end ETL with data in the Hadoop ecosystem, and ETL stands for extract, transform, and load. So basically working with data in a Hadoop ecosystem, that requires a whole nother course of training, which we're not going through now because not every company uses Hadoop. You also won't be able to work with AWS instances and productionalizing your ML models made with PySpark. So AWS, again, if you've seen, it's at the very end of this mod. I won't be doing a study group on it just because it links to the AWS tutorial. That will be better than anything I can tell you about AWS. So if you're interested in that, that is there. And you won't be able to do this because all of these frameworks involving Mapreduce, Docker, PySpark, and distributed systems in general, very, very technical and specialized. Like, I think the keyword here is they're very specialized. Only if you want to get into the big data space, which not every company does, only if you want to get into that space, then it might be worthwhile looking into like getting used to like working with Hadoop and PySpark. So we'll only get a high level overview just so we're aware of some of like the terms and lingo that are being used.
Yeah, however, one quick question. Can you explain the Mapreduce job again?
Yes, I have like a few slides talking about what Mapreduce is later on.
Okay.
But if there's any word they'd take away, yeah, just remember that Mapreduce is a thing with big data. And yeah, probably if you ever were to get asked a question on big data, and I have never for a data science interview, unless it's for like a position that works with big data, then yeah, you should prepare this. But if there was any question they would ask is like, how does Mapreduce work? And I will go through that in a little bit too. All right. So what is big data? So big data, I feel like that word gets thrown around a lot, right? Like, I don't know, with people are saying that like we're in the age of information right now and a lot of data is being generated, but what exactly is big data? So it's not just, you know, a data frame with like a billion rows. That does not necessarily mean that it's big data. So big data technically is characterized by the 3 V's. So volume, so yes, your billion row data frame, velocity, and velocity just means that you actually have data constantly streaming in at some speed. So maybe you have data on like the weather that's being recorded on a every minute basis, and that information is consistently being added to your database. That is a characteristic of big data. And then variety. Variety being like, imagine the kind of data that Facebook possesses, right? They don't just have your personal information like in text form, but they also have all your photos, videos. Now apparently Facebook is being used as some sort of streaming platform, so they have that data too. And so big data is also characterized by its variety. So main takeaway here is if you have a 1 billion row data frame, it is not technically considered big data just because it doesn't have, you know, the velocity and variety components. Questions about this? All right. So next up, why do we need distributed systems? So distributed systems we'll get more into in a little bit, but the idea of distributed systems is basically taking the work that you're doing and splitting it across multiple computers or multiple servers. So just a bit of quick math. How long would it take for 1 terabyte of data to be read on a hard drive? And reading data is really just like doing pd.read CSV, right? All of our data files that we've been working with are like in the megabytes. But if you had big data that existed in 1 terabyte on a regular like 100 megabytes per second computer, it would take almost 3 hours to just do the pd.read CSV step. And that doesn't include the part of like rendering the pandas data frame, right? It's just having your computer recognize 1 terabyte of data. But of course, if you split this work across 10 systems, I believe, I keep forgetting to change this, but if your speed is at 1,000 megabytes per second, it'll take 17 minutes. Oh, right, it's 1,000 megabytes per second because each computer is doing it at 100 megabytes per second. 10 computers, that's the kind of speed you get. It'll take you 17 minutes. If you have 100 systems, what's this? A little under 2 minutes. So obviously, you know, you have more workers working on the same job, the job will get completed faster. And with big data, because of the sheer like volume and velocity, you need distributed systems to process what data is coming in. Questions before we start getting more technical?
So by distributed systems, basically just mean it's lots of computers are working on it at the same time.
Yeah, and part of like the Mapreduce procedure that we'll talk about later is how do you do like one process? How do you like split it across multiple computers, and how do you aggregate all of it back together? And that's something we'll talk about later too. But yeah, this is really just distributed systems is just, let's say I want to count all the words in all of New York Times articles ever written. I probably won't be able to do that on my computer in like a reasonable amount of time. So I'll split this work amongst like 10, maybe 100 computers. Anything else? All right, so let's introduce Hadoop. So Hadoop is a distributed computing system and environment for very large data sets on computer clusters. The way I like to think about Hadoop that helps me understand it better is Hadoop, it kind of provides the architecture for splitting up your work across multiple computers. So later we'll talk about Spark. I like to think of Hadoop being the hardware and Spark being the software. It's not exactly like that, but that's an analogy that helps me understand. So the elephant is Hadoop's logo, just in case you're curious. And yeah, Hadoop, basically, if you want to run a program or like a function using distributed systems, you probably have to use Hadoop, or there are actually a couple other companies that do the same thing, but I think Hadoop is the most salient one. So more on Hadoop. If you're using Hadoop, you're using an entire ecosystem with it, because Hadoop by itself is just like the hardware component. It's just like the multiple servers that you split your work across. So we have to go through some definitions here. HDFS, which is this lower layer here, that's the main Hadoop part. HDFS stands for Hadoop Distributed File System. So Hadoop is the company, HDFS is their product. It allows us to distribute data across a cluster of computers. So again, like the hardware of your different computers, making multiple hard drives in our cluster function like a singular file system. So when we say a cluster of computers, that's basically like multiple computers. So HDFS is the architecture that allows us to use multiple computers as one computer. On top of HDFS, honestly, this part's a little bit less relevant. You can sort of think of it as like a middleman. It's called Yarn, which stands for Yet Another Resource Negotiator. So Yarn is a layer right on top of HDFS. You can see here, I hope y'all can see on your screens, but this is Yarn. And Yarn deals with the data processing. So Yarn is the part of HDFS that decides what each node, and each node being which computer, what each computer runs and when. So for example, if you're running multiple processes, let's say one, I want to count all the words in the New York Times articles, but also I want to maybe save every image that comes with a New York Times article. And let's say I want to run these two processes, what Yarn could do is say, all right, maybe let's allocate like 10 computers to do like the word count and maybe 5 others to save these images, just as an example. So Yarn is kind of like the executive, the delegator, and it's known as the heartbeat that keeps the cluster running. So other resources like Mapreduce, which as you can see here, this is Mapreduce, and on the level of Mapreduce is Spark. So Spark is what allows us to use Mapreduce because we are trying to execute functions within Spark or PySpark, and the functions utilize Mapreduce. So this is kind of like the layers that exist in the Hadoop ecosystem. Questions at this point? I know there's a lot of like new words and new ways of thinking, but yeah, questions.
One quick question. So if I remember correctly, like when we are using Spark, right, Yarn is automatically taken care of, right?
Yes. I feel like Yarn would have been taken care of. Honestly, I am not the most hardware oriented person. So I don't, the way I think of it is Yarn is more of a component of HDFS, and then Spark is on top of that. So yeah, if you're using Spark, you probably already have Yarn. Yeah.
Yeah. Okay.
Yeah. Kevin, I saw you might have a question.
Yeah, there's these vertical brands and logos that are sort of spanning multiple tiers. Are these like products that handle all of it within one product? Or
yeah, so kind of. I don't know all of these, to be honest.
That's
but
fine.
I know Apache. Apache does have all of these layers.
Okay.
Apache, and actually Spark is built by Apache.
Yeah.
So so Apache does handle like the file distributed system as well. Kafka I've heard of as well, and I do know that Kafka does do at least the HDFS component and the Mapreduce component. All the other things, I don't know what either of these two are, to be honest. Yeah.
Cool. Okay. Thanks.
But
That
yeah,
answers
these
my
are all,
question.
oh, okay, great. Yeah, these are all different companies and
Yeah.
basically their products will work with each other. Yeah, anything else? All right. So let's get into Mapreduce. So the whole idea of Mapreduce, as I kind of alluded to earlier, is divide and conquer. So instead of just using one system to perform a task, Hadoop and Mapreduce allow tasks to be divided across multiple systems. So we'll get into more detail a little bit later, but tasks are first split into many subtasks. And again, it does depend on what the task is. And we'll get into more of those details in a little bit. These subtasks will be solved individually by the different computers that you're using. And then there's some aggregation step at the end because you ideally don't want 10 separate results of word counts from like different subsets of New York Times. You want a complete aggregation of all of that. So Mapreduce will split your tasks into subtasks and then allows them to be processed in parallel. Mapreduce has two main phases. First, you have the mapper phase, which is the part that transforms your data in parallel across all the nodes in your computing cluster in an efficient manner. And we do have some examples in a little bit. And then there's the reducer phase, the aggregating your entire data and returning a final result. There are some, There are some drawbacks to this, and we'll talk about them in a little too. This, not super important. I put this here just so y'all can see like it is written in a different language. It is not Python, which is what makes it hard for us to write Hadoop jobs. And I'll get into more detail about that in a little bit too.
Just out of curiosity, is this anyway compared with the scaling part of it, which we did in the last project?
Scaling part of it. No, I don't think so.
Okay.
Yeah. But basically what's happening here, this is basically doing a word count. I know that you're like counting all the words up in some document, and then here you have to take all of the word counts from your individual computers and then aggregate them together. So you can imagine for doing something like a word count, what it would do is I don't know the exact subtasks that are written, but I can imagine that for a word count, you would maybe give like 10% of your data to like 10 computers each. And then they'll each count up the number of words. And then the aggregation step is just summing them all together. Something like word count is easy because the aggregation step is just adding them all together. But you can imagine some other things like, for example, running an XGBoost model or any boosting model where it's a sequential process. That aggregation step becomes a lot harder because you imagine with XGBoost, it does matter the order of your trees that are being trained. How does that work across 10 computers? I personally don't know how they're doing it. But you can imagine that the processes of the aggregation process is going to be much more complicated than that. All right, so another like image form of how Mapreduce works. Basically, your inputs are split up. Typically, your inputs are going to be your data inputs are going to be split up across multiple computers. Some function is being done here to, like, for example, filter transform data. Usually, there's some shuffling step just so you make sure that I like to think of it as such that there's no overfitting on a certain computer. It doesn't apply to every single function that you're doing with Mapreduce, but yeah. And then you have some aggregation step and you get a result. There's another image that pretty much shows the same thing here. In this example, we have word count with Mapreduce, which I talked about earlier with the example of New York Times, but here's a simpler example. So let's say that in your big data set, you have these 9 words. You're gonna split it across 3 computers. So you're just gonna randomly split it into 3 computers, do your word count. So here you can see deer, bear, river, car, river, deer, car, bear. They are counting up all of the words here. They're gonna reshuffle it. Again, the reshuffling for word count doesn't really make sense. It doesn't really value add in my opinion, but they're doing it anyway, reducing your result to to, oh, I guess in this shuffling, they're like reshuffling to sort it. I don't know if that happens with every algorithm, to be honest, but there's some step of re-aggregating everything together. Questions about this?
Yeah, so is the splitting working like the on the hyperparameters you just mentioned that, okay, how many computers you want, like you mentioned n jobs, saying that how many cores you wanted.
Okay. I would say, yeah, that's kind of similar. Yeah, in a similar way, like how many cores on your computer you're using, that n jobs hyperparameter that exists in some models. Like I know Random Forest, I think Random Forest has it. At least definitely XGBoost definitely has it. So yeah, in a very, very similar way. Yeah, you're just splitting your work across more cores for your computer.
We are doing it online, right? This is going to be right. How the internet speed is going to affect that?
Oh, that's a good question. I do not know. I have no knowledge on like how internet speed works with the cloud. My assumption is if your internet is not good, you probably will not be able to get a good connection with whatever remote server, but I cannot tell you with confidence what I know about internet and how, I don't know how internet works. But yeah, I imagine if you don't have internet, you can't work on a cloud.
We will figure it out when we get stuck for hours.
Oh, I will say as well, like as it is something that you do set up when you set up like whatever thing you're doing in PySpark, you do have a step of telling it how many computers you want to split your work up into. And I believe I have some sample code as a screenshot in here, and I'll point if I have that there, I'll point to where it is. If not, it should be commented in your lessons. Any other questions? All right. So beyond Hadoop, and this is where we're going to actually lead into Spark. So even though Hadoop speeds up processing tremendously, there are a few problems. So again, like what I mentioned previously with like the XGBoost example, if the algorithm is iterative and it works by iterating on itself, splitting the work up doesn't necessarily help. So that's one drawback that Spark actually helps with. And also Hadoop jobs are mostly written in Java, which can be painful and error prone without expertise, making it less accessible. I don't know if anyone's ever tried looking at Java code. It is a lot of parentheses and at least for me who started learning with Python, it's much more convoluted and harder to pick up. But I mean, definitely get used to like seeing some of like the structures. I would say that's one thing to do after graduation. Just take a look at some of the syntaxes of other languages, just so you're familiar with what it looks like. So yeah, that brings us to Spark. And Spark, this is just code from Spark. And this is just showing that Spark has incorporated a lot of optimization for a lot of tasks. So Spark jobs, and in the next slide, I believe in the next couple of slides I have this, but Spark basically, they have a lot of built-in functions, or you can import libraries in Spark that have methods that are optimized for working across multiple computers. So for example, the XGBoost example, they've basically figured out an efficient way to work around the fact that the algorithm has to iterate on itself. I will tell you that the algorithms themselves and the math that goes behind it, very, very advanced. Like I have no idea what it looks like.
Is that
it will work on the
slide? You were talking about the ability Java. That looks like JavaScript to me.
That is, so this is actually, this is not JavaScript. This is actually PySpark. And we'll talk about PySpark it's PySpark, which is actually, technically it is written in Python. And so here you can see that just some of the methods are different. So this is actually the same as doing like a pandas.read. Can you read text file? I forget if there's a read txt, but similar to that. And then these are basically using methods. So here you are I think .map is one that we're familiar with. So if you're mapping a function, we've used map lambda, where you like map a function onto every element in a data frame, for example. But yeah, you can see here that there are some other methods that you have to do that, like, this is the reduce step, basically. The map and then the reduce step all in one. So if anyone's curious, this is basically reading some text file. You're splitting the text file by the spaces, doing a word count, and then reducing the word count just to get the overall word count. I will say, like, the specific methods for now are not very important unless you really want to figure out how to work with PySpark. But a lot of the methods you'll walk through in like the Learn Labs. Anything else before we move on into like more details about Spark?
I was going to ask you, will this help like with those the plotting of the decision trees, which forever.
Mhm.
So would we be able to write some kind of code on Spark and then it will be like doing the process or mapping it faster?
Well, first, I imagine that plotting the decision trees, one, I know it takes a long time on your Jupyter notebook. So Spark would likely make it faster. I will admit that I don't know if there is a plot decision tree function that exists within PySpark. So within PySpark, and we'll actually take a look at some examples later, you will not use like your typical pandas libraries. You wouldn't use pandas, you wouldn't use scikit-learn. There are PySpark versions of these though that are optimized to work with the distributed file system. So the syntax is slightly different, but it's really just a matter of like looking up the right word to do a specific task. And I'll show you some of the parallels later as well. But yeah, I imagine if you were to do the plot decision tree, I think a big drawback of plotting the decision tree is that you just cannot see the entire decision tree in a cell output. But I imagine it will be a lot faster on a distributed system. But to be honest, I don't know if there even exists that method on PySpark, just because you imagine with the big data they're working with, probably the trees that you're going to be building are going to be much bigger. So you could argue that, visualizing those decision trees are not going to value add as much. Anything else?
No.
All right, let's talk about Spark then. So advantages of Spark, it's more fault tolerant. One, a lot of the methods within Spark or PySpark have been optimized for Python users. Also, the error messages that come out are very similar to the Python error messages that we see. It's a higher level query language, so you can implement SQL-like semantics on top of Mapreduce. Basically, if you want to query like giant databases, you can use something like SQL or a SQL-like language to query that data. Spark is also optimized better for iterative algorithms. And I actually have like a screenshot of an example of like running, I believe a decision tree. But yeah. And also Spark jobs are even faster than traditional Mapreduce, just because the way it's built and a lot of the functions that are built in Spark have optimized for a lot of these like iterative algorithms and basically like machine learning algorithms. So PySpark, right? So PySpark is a subset of Spark. Spark is actually available in many different languages. So with these points, Apache Spark is by the company Apache, is written in Scala. Scala is a language that is actually, I have tried to learn Scala. I know a little bit of it, and I would describe it as like a cross between Java and Python. It uses a lot more object-oriented programming, and you have to define things a lot more clearer. So if anyone's interested in Scala, it is very fast. It's much faster than Python. But I will say for data scientists and their first, second jobs, you probably don't need to use Scala. So Scala is a general purpose data processing software that offers APIs, and by APIs, we just mean methods that are written in Scala, Java, R, and Python. So to help support Python with Spark, they released PySpark, which has a similar computation speed and power as Scala, which again, much faster than doing something on our Jupyter notebook. And then PySpark's APIs are very similar to Pandas and scikit-learn. In a couple of slides, I do have examples showing those similarities. Questions about this so far? Okay. So with PySpark, you'll see some of this terminology come up, Spark context and RDDs. So PySpark has Spark context, which is an entry point into the world of Spark via Python. Very similar to using a cursor to connect to a SQL database. So remember when we were working with SQL, we always had like the cursor.execute, whatever it is. That's similar to Spark context. And I think I have, I'm not sure if I have it here, but here, I'll talk about this later then. So there's Spark context, and that's something that you just have to instantiate at the start of when you're working with PySpark. And then you also have resilient distributed data sets, RDDs, which are the fundamental data structures of Spark. So I think I have that later, but RDDs are essentially the Spark representation of a set of data spread across multiple machines, and APIs will allow you to act on it. So RDDs are to PySpark what Pandas data frames are to Jupyter notebooks, and we'll actually see how similar they look in a little bit. And similar to Pandas data frames, RDDs can also be come from any data source. So you can upload text files, SQL databases as well, JSON files. You can even connect it to like a constantly streaming database. So the information will be put into RDDs if you're working in PySpark. So RDDs, which stand for Resilient Distributed Datasets, they are just that. They're resilient. They're basically they have an ability to withstand failures. They're distributed. The whole purpose of us doing this is that they are spanned across multiple machines, and they're data sets. You can pretty much put any sort of like table-like data into RDDs. So arrays, tables, tuples, basically anything you can put in a Pandas data frame will work in an RDD as well. So how to create and work with an RDD. So here's some of the things I want to point out. If you do decide to work on the PySpark labs, these are some of the things that you'll see. So whenever you start working with PySpark, you will have to first build a Spark session. So it's sort of like your PySpark session, and that's where your Spark context is. So here you just have to like define some things. All of these configurations, they'll explain it much better in your lessons. But here you can see you're using Spark context, which is your entry point into the world of PySpark, and you're going to parallelize your data. And this step of parallelizing is the step that is distributing it across different systems. I do believe, and I'm not sure if it's exactly in this step or in a separate step, you get to tell it how many systems you want to spread it out across. You definitely see those in your labs, but there is like a place where you tell it how many systems you want your data to be spread across. Of course, with this small example here, there's only let's see, 4 columns and let's wait for this to go away, and 3 rows. And you can see here as well that yes, it's a data frame, but this is an RDD, and the way it shows up is, I mean, it doesn't have that nice interactive look that Pandas has, but it does show up as a table this way. So if you're working and doing functions, and let's say you want to like filter your RDD, you can like show like your first 5 rows, and it will look like this. Questions?
Would you be able to go back and forth between a RDD and a Pandas data frame? Like, are there ways to transfer between the two?
Oh, that's a good question. So you can definitely still like import pandas while you're working with PySpark in the same notebook. In terms of like having them communicate with each other, I wouldn't be surprised if there is a way to do it, but not something that I'm familiar with.
Okay. It's not commonly
yeah.
done, I guess.
Yeah, because usually if you're working with RDDs, you have big data, and then and data frames are typically known to be actually quite slow in relatively. But yeah, I wouldn't be surprised if something like that exists. I'm honestly not too sure. If anything, you could like feed in, I imagine you can definitely feed in like your data frame in some form here. Maybe you have to like turn it into an array or something. But yeah, not that I'm aware of, to be honest. Again, wouldn't be surprised if there is. If not, both of them have like an export and import option, so you could always do that too. Like export like your RDD as a CSV. I don't know how big that CSV would be, but and then yeah, like read it into pandas or the other way around.
So now let's say when we import, when we are doing the read CSV part, uh, so is there an alternative here? And like it says that PySparks dot read CSV.
Yeah, there is. I honestly forget what it is. I don't know if I have that as an example here. Yeah, I don't think I have an example here, but yes, there is 100% the same thing in PySpark. Like if you have a data file.
Yeah, the reason I was asking is like, say the file of 350 MB. In my system, right, it actually got crashed quite a few times when I was working on the data. Now, let's say if I work on the same data in PySparks, then I'm assuming because it's doing a lot of things and it's online, then it may not crash.
Oh yeah, yeah, it definitely will be able to handle much bigger data sets. Like I think the lab that they have you do is a file bigger than 300 megabytes. I think, I don't remember if they've changed it to something more manageable, but yeah, you can definitely do it in PySpark because PySpark has much higher limits on your data file size. And plus you're not running it on your computer, you're using a remote server. So yeah, there's definitely like their version of read CSV. I just don't know what it is off the top of my head. Any other questions? All right, so with RDDs, how do you create and work with RDD? Main steps are you're gonna have to parallelize whatever your data is, and you can work with any external data. So one thing that you can do is you can actually, if you have the architecture set up where you have Hadoop already, you can actually store your big data files in HDFS, whether it is in like a consistently streaming large SQL database, or maybe you have like a consistently updated like JSON file, stuff like that. You can read in that file from your Hadoop system. Or you can also work with objects in Amazon S3 buckets. And S3 buckets are basically like, you would use S3 buckets, and I would actually like talk about how you could set up S3 buckets in the capstone if you have like very, very large, I'm talking like gigabytes large data sets that you can't store on your own computer. You can actually store them on Amazon cloud. And also the simplest example, which is the example that I know that you have in your lessons, is lines in a text file. You can basically read any data into RDDs. So yeah, with RDDs, some of the operations that you'll see, and I'll basically talk about like how they are similar to pandas methods. So one group of methods that you have are transformations. So with transformations, you can take your RDD and then just return a new one. So basic transformations, you're going to be using the map and the flat map functions a lot, because basically that's how you broadcast methods across every row in your data frame, or every row in your RDD. So your labs have actual concrete examples and and they have you run all of these. But just as a quick example, flat map will do multiple values per element. So if you ever had to do, like, for example, here, this method of splitting each sentence by its space, you would use flat map, because flat map will allow you to return multiple values per element. And map, you would do map for something like, I think if you were to do like a count, you would use map to count. And then dot filter, same thing as pandas. In pandas, you can filter. Here you can filter as well. Just so you see some of these, you can also do actions. And again, like all the ones I'm talking about, that's not it. I mean, just like how pandas has like hundreds of methods, so do RDDs. So some of the actions that you can do, and ones that are going to be most useful, where we do like a pandas, when we just display a whole data frame, if we want to display a whole RDD, you would use collect, although usually your RDDs are going to be so big that you wouldn't use this. But yeah, if you want to return all the elements of a data set as an array, use the collect method. So you literally will do like RDD dot collect, and all of your things will display in like this format down here. And then you have take. Take is basically dot head of our pandas. So if you do like RDD.take5, that's like getting the first 5 rows of your data frame. Dot first element, dot count returns the total number of elements that you have. So as you can see, like the kind of methods that you would be performing on RDDs are very similar to the methods that you will perform on your pandas data frames. Questions at this point? All right. So use cases for Spark. Again, Spark is good at dealing with big data. So if you're streaming and analyzing data in real time, usually what people do is you would build an ETL pipeline. So an extract, transform, and load pipeline. So for example, let's say you get like raw data of, I don't know, everyone's Twitter feeds, for example. And you wanted to do, oh, we'll get into this with NLP, but let's say you wanted to do like a word count for everybody's tweets as they're coming in, part of your ETL pipeline. And let's just assume like the data that you want to collect is, let's say, metadata on the tweet. You want to get like the time it was written, location if there's any, and like the username. And then you just want to get like how long the tweet was in terms of like number of characters. You would build a pipeline that as data is streaming in, it would collect all that information and put it into your RDD. On top of that, not just like the pipeline part, you also have data enrichment. So definitely if you're working in a database, you have some static database where is your base database. And then, for example, every day you're enriching that database with new information. So yeah, that's the process of data enrichment, is just the adding on of new data points. I think it's in the next, oh yeah, the next slide I have is the last slide. But yeah, you can also perform machine learning tasks. And again, they are very optimized for working across distributed systems. The library that you use instead of scikit-learn is called MLlib in PySpark. And what it lets you do is perform tasks like ML modeling. Basically, pretty much, I think almost every every algorithm we've talked about in this course will be within MLlib. So you can do ML modeling, any of the classification regression algorithms that we've talked about. Market segmentation, that's pretty much like clustering analysis. Sentiment analysis, which we'll talk about when we get to NLP. You can also build recommendation engines. One example is actually in your recommendation engine section. You can actually do, there's a PySpark version of that. So yeah, you can build all of these within PySpark as well. The method names are slightly different. I'll show an example in a little bit. And then finally, you can also do interactive analysis in Spark. So imagine as you have data that keeps coming in and you have like a data dashboard, like maybe you have summary statistics on all of your data. Maybe it's represented in like bar charts, pie charts, I don't know, line graphs. Because Spark supports data that's consistently streaming in, those visualizations will update as you get new data. So Spark actually does support that, but you do need additional you will need to get into the visualization software within that, which I personally have not used before. So just really quickly wanted to show you all, this is literally a screenshot of training a decision tree within Spark. You can see that it's similar, but just a tiny bit different, right? So here, this is literally instantiating the decision tree and fitting it onto your training RDD. So here you can see that the instantiation step is with the fit step here. You have I don't know, your number of classes. The things that you define are going to be slightly different. So that's why it's important to look up the documentation as you're putting this together, especially since it's different from what we're used to with scikit-learn. But yeah, it's actually a very, very similar process. You're fitting your model and you use your dot predict here. And here you can see that we're actually using the map because it's important to have that Mapreduce step there. And yeah, you can do all the same things. You get your overall accuracy metrics. You can even plot a confusion matrix if you'd like. And this down here, this is like the text output of a decision tree. So basically you can see that this is telling you if you have a certain data point, just traverse the tree with these if else statements, and that will give you your prediction. Yeah, this is a four layer tree with 21 nodes. But yeah, the processes are similar but different. It's just a matter of like, if you want to really get to PySpark, it's just a matter of getting used to the different syntax that they use and the different like names of, I don't know, methods, and the different way they take an argument. So that all you can get from documentation. But the way the decision tree works here, exactly the same. The only part that's different is the way that they are splitting up the information and reaggregating that. That part, I honestly also don't know how they're doing that. But the idea of a decision tree still holds. Like it's still doing the same thing as like segmenting your data. But yeah. All right, this is my last slide. So any questions?
Just one question. Like, so let's say when we are doing the multiple models, and if you want to convert into a data frame, right?
Like your all of your like modeling results.
Yeah. So then what we do, we just we go back to pandas and use data frames, or like.
Oh yeah. Yeah, that part definitely, because here you can see that, you know, you're saving your accuracy number as a variable here. Within this, you can also import pandas and then just stick it all in the data frame together. I will say it will be harder to be like writing functions to like functionize all of these processes. That I'm honestly not sure, like in the real world, how people do this in Spark, just because the people I know don't use Spark, honestly. But yeah, I imagine if you wanted to do something like that and like collate all of your results in one place, you can definitely do that here.
Right.
Anything else? Again, if there's anything you take away from this, it's the idea of like, you know, with these distributed systems, Mapreduce is the overall thing that's being done here. The fact that you're splitting up your work across multiple places and aggregating them together. Other than that, I mean, Mapreduce is used in other technologies, not just, Spark is not the only technology that makes use of Mapreduce. So yeah, I will say like you might come across, I can't even name another company off the top of my head right now, but you might come across some technologies that wherever you end up working at are also doing big data. That was not an English sentence, but yeah, you could be working at a company that also works with big data that doesn't use Hadoop. So yeah, just be aware that Hadoop is not the only one out there. Any questions to close out? All right, well, in that case, I will see you all on Monday. On Monday, we're going to go through recommendation systems. I'm not sure if I've updated the calendar yet, but recommendation systems is on Monday. And then, oh, sorry. Yeah. Thank you for reminding me. Monday is a holiday. That is what I wanted to talk about. Monday is a holiday. So our study group will be pushed to Tuesday. Same time. That will be recommendation systems. And then after recommendation systems is 2 sessions of time series followed by 2 sessions of natural language processing. So yeah, that's what's coming up. And after natural language processing, it's just neural networks and we're done, which is crazy. So yeah, look forward to all of that. As we're starting to get through like some of the big topics for the phase 4 project, again, I just want you all to keep in mind that for your project, you'll be only working on one of the 4 topics. So feel free to like just focus in on the one that you want to focus in on. Most students don't do all of the material. Most students actually do like 1 in-depth, maybe 2 to prep for capstone. And then the rest they either, like for example, some students decide that they don't want to do anything with NLP ever. And so I can't force you to learn it if you don't want to. So yeah, just be aware of that you have some flexibility here. All right, then. Have a good night, everybody. And I'll see you back here on Tuesday, if not at your 101s. Bye, everyone.
Thanks. Have a good night.
You too. Bye.